Okay, then as usual, let's wait until exactly my clock chimes 6 o'clock. Okay, my clock chimes. So let's start. Okay, so again, let's recap and do the review. So remember, previous class, we started the formulation of adaptive control using only input-output measurements, right? Of course, ahead of that, what we needed to do was, first of all, to post the methodology of positive real transfer function and related with it the Kalman-Yakubovich lemma, right? And with that, of course, we made sure that we had all the suitable supporting mathematics ready, right? Then, of course, with that, we began to pose and formulate this problem of adaptive control using only input-output measurements. And remember, I developed that in a very compact way using the differential operator. But I also warn you, I said, it's okay to do that, but make sure you do that very, very carefully, observing all rules, right? And you recall how we did that, right? If you go to what we had done, right? We said basically, okay, essentially give me the equivalent of this system that you're trying to control, right? Essentially equivalent to a transfer function, pole polynomial of order n with all these coefficients. Leading coefficient is 1. Then, of course, also the zero polynomial, right, of degree m, and also leading coefficient 1, right? Then we said, okay, there's this fancy name given to this type of polynomials where the leading coefficient is 1. We call them monic polynomials. And what happens is that here, this one is always possible to do because what we do is we pull up a number called Kp. All right, because as you pull up this number Kp, clearly you can write it in this form, right? Then we also label the integer number n star, which is basically n minus m, which is called the relative degree, right? Then I said, okay, with that you can introduce in this identity, which goes by many famous names, Diophantine identity, Bijou identity. But as I told you, I mean, it's basically equivalent to polynomial division, right? Because here what you're saying is that you give me a monic polynomial of degree n, a monic polynomial of degree n star, and that you can always write it out in this decomposition. And of course, because Rp, which is the pole polynomial above, is of degree n. And you can think of the fact that on the left-hand side is a monic polynomial of degree n plus n star, right? Divided by a monic polynomial of degree n, which is the divisor, right? And of course, the quotient will be of degree n star, all right? And the remainder will be of degree n minus 1, not necessarily monic, right? So, but it's important identity, and whoever first observed that should be given credit for that. Right, and then with that, what we said was that, okay, now if you handle your differential operator developments carefully, you can essentially rewrite the system, right? So to begin with, the system is the Rp polynomial operate on y equals to Kpzp operate on u. Then we say, okay, sure, based on this division identity, essentially, all right, I take this E, which is of degree n star, right? And then I operate on both sides by this polynomial E. And as I told you, I say you watch it carefully. These are linear time invariant polynomials, all right? And if I operate by a polynomial E of degree n star, which is also itself linear time invariant, okay, I do not violate any of the conditions of your linear systems. All right, so superposition is obeyed. Commutativity, associativity is all obeyed, right? So therefore, you can do that. But as I told you, I said be very careful because there have been attempts to do adaptive control directly using this, and it really looks scary and wrong, as I said. Okay, so anyway, here we're very careful. With that, we have this. Then, of course, since I write it like this, I can go back to the polynomial identity, correct? And use it and rearrange. So now what I have is TRM minus F operated on Y equals to K E ZP operated on U. All right, then I collect this together. E is monic of degree n star. ZP is monic of degree m. I can call this of a G polynomial of degree G bar. All right, and you will see this is of degree n is monic. Okay, then T Rm as from above minus F. F is of degree n minus 1, not necessarily monic. Okay, then let's begin to look, rearrange, then we get RMY. All right, and then of course the other side with the G bar. Then what I also do is I filter both sides by 1 over T. Okay, I can do that, but you have to be very careful. The moment you filter both sides by 1 over T, straight away you have to introduce the assumption that T is a stable polynomial. All right, T is Hurwitz. Okay, that's possible to do because the moment you filter both sides by a stable polynomial, it still works out correctly. All right, and then you rearrange, and it looks like this, right? And at this point, we say, okay, let's observe carefully. This is of degree n star, which is n minus m. This is of degree m, and this is monic, right? So clearly, I can take this whole thing and expand it out as 1 plus G1 over T. All right, T, remember, is of degree n, monic, but already from the above assumption, it has to be a Hurwitz polynomial. Okay, now G1, the moment you write it out in this way, G1 is of degree n minus 1, not necessarily monic. Okay, so we go on further. We say, okay, now let's rewrite it out. G1 is of degree n minus 1, not necessarily monic. I can write the F bar down here because I take the original F, which is of degree n minus 1, not monic, not necessarily monic, and with that I pull up a KP, so I get n bar, which again is of degree n minus 1, not necessarily monic, right? So I can write F bar like this. Okay, then the moment I write it like this and I look above and say, look down here, this is what I have basically redeveloped the equations into. Then I say, okay, let me now look at this equivalent one. And I said, look, is there a possibility for me to take whatever is inside here to make it exactly equals to K star R? Because if indeed I can exactly make it equals to K star R, then essentially now with all this thing down here, I basically have made it such that the equivalent system that result from making this equals to K star R is RMP equals to Y equals to KP K star R. And RM will be something you choose. All right, you can choose it. You will choose it to be Hurwitz of degree n star. All right, so this is what's going to happen. And this is what happens if you can perfectly make this control law happen. If you can perfectly make this control law happen. All right, we back off a bit. And I say you look carefully at these numbers down here. All right, and if you now backtrack, and look at everything on how we have done carefully, if you backtrack, you will see that, okay, if you backtrack all the way to right in the beginning, all right, where we pose the problem, all right, if you backtrack to here right in the beginning where we pose the problem, and if you assume that you know all the numbers A1 to AN, all the numbers B1 to BM, and also this number KP, which is what you would do in standard control, all right? What you would do in standard control, because you will work with a system that you know, all right, and KP, and then if you know that, then go through exactly all these things. Do all these things exactly, calculate, and you will see that if you started off knowing the system exactly, all these numbers G1, G2 to GN, F1, F2 to Fn are numbers that you can exactly calculate. Numbers that you can exactly calculate. Okay, you will be doing this in your CA1. Of course, in your CA1 is simulation. So I give you a system to simulate, to say you have to control this system. But since you're simulating this system, clearly you know the system, and then you can calculate and exactly know what these numbers are. All right, except you should not be using these numbers because you're supposed not to know the system, just to simulate it. Okay, but anyway, you can reverse calculate, you will know all these numbers. Okay, so now, all right, in the event that you know all these numbers and you want to make this control law happen, I say, okay, let's see how we will make this control law happen. All right, because this is actually your perfect control law, so to say. Okay, so I said, okay, look specifically at the case for n equals to 2, which is actually exactly what you're doing in your CA1. Okay, exactly what you're doing in your CA1. Okay, so as I said, you reverse calculate, you know exactly the number F1, F2. You know exactly the number G1, G2, because you're simulating. All right, you know those numbers, okay, except you're not supposed to use them, but these numbers, if you actually wanted to calculate, you know them. So anyway, with n equals to 2, this is the F-bar polynomial, this is the G1 polynomial. You will choose a T polynomial. This one you choose. All right, you will choose this to be Hurwitz. All right, then as I said, the moment you choose this, you told me I can measure the output signal. So I measure the output signal. I pass it through a 1/T filter. All right, and T is what I choose. I choose this to be Hurwitz. You need to think about how to properly choose it. All right, the bandwidth and things like that when you set up your adaptive control system. But from a theoretical viewpoint, the only requirement is that it should be stable Hurwitz. That's all. Okay, but when you go and work on your adaptive control, well, which is actually close to what you will actually do in real situation, you have to think on how to wisely choose the T so that basically your performance in your system will actually look quite good. All right, your choice of T would affect your performance. All right, it will not affect the stability. Stability is guaranteed. I will show you. It will not affect the guaranteed convergence of the tracking error also. That's guaranteed. All right, so convergence error, I will show you, is guaranteed. Overall system guaranteed. All right, from a global viewpoint, no matter where you start. All right, but basically how it reaches that convergence does depend on your choice of T. That one I'll get you to simulate and study in CA1. All right. Okay, so anyway, you choose this T, and then you take the Y, pass through a 1/T filter that you choose, call the resulting signal omega sub Y. You can set this up as a state variable system, control canonical form. All right, very straightforward. You can set it up. Okay, and it will look like this. Similarly, you told me you can measure U. Of course, you can measure U because you are the one computing and using it, so you can measure U. So similarly, you also construct a 1/T filter, pass U through it, and call the output as omega sub U. Similarly, set it up in controller canonical form. All right, very straightforward. And you get this. Okay, most important thing is that for the first set where you put in Y as the input, this is the signal that comes out. When you set it up in controller canonical form, these two are your state variables, all right, coming out of your state variable filter down here, first one. All right, and then when you set up your U, okay, these two are your state variable filters. These two are your state variables coming out of your state variable filter here associated with you. Okay, so as I said, okay, go and carefully check. You need this signal. When you go and rearrange it, you'll find that, okay, it is F1 times one of the state variable signals from your first state variable filter with Y as the input, okay, and the second state variable also from the first state variable filter that you set up. Okay, so just a gain times whatever you're getting out of your state variable filter, another gain times whatever you're getting out of state variable filter. Similarly, okay, the other one, okay, you expand it out, it will be G1 again times a signal coming out of your second state variable filter, G2 again times a second signal coming out of your state variable filter. How does that look like in a diagram? It's exactly like this. All right, and as I said, this diagram, which is what I left you with last week, is very, very important. It has very far-reaching implications, all right, which I simply left the diagram at that stage, all right, and asked you to think about it. We will look at it further this evening. All right, basically you're saying you have this system that you're trying to control, all right, input signal you have, output signal you have, okay, and that's all you have. Then you say you set up the 1/t filter with Y as the input. You set up the 1/t filter with U as the input. So these two signals came out as we saw. All right, then remember we exactly multiply them by these gains, F1, F2, G1, G2, and then you put it back down here with a minus sign. There's a minus sign. All right, then you take R and put K star. Okay, as I remind you, all right, these numbers, these perfect numbers, they exist. All right, and if you knew exactly what KP is, all the numbers in your zero polynomial, all the numbers in your pole polynomial, if you knew all these things exactly, you can reverse calculate exactly what is F1, what is F2, what is G1, what is G2, and what is K star. All right, so this can be exactly calculated. All right, so put them in, this exactly calculated one. And when you put these things exactly calculated one in this way, you can see that, all right, now this exactly, okay, exactly for your second order system, exactly does this for you in the case of a second order system, which is your perfect control law that you want. Exactly does it. Okay, so that diagram there exactly constructs for you this so-called perfect control law, which now answers for us the first direct question, because as I said, the first direct question is you write all these perfect control law, is it possible even to implement or not? So clearly this is possible to implement, because clearly, you know, in real life, okay, in real life, you have the system that you're trying to control. There's an input signal, output signal in real life, all right? So it's not simulation anymore. All right, in real life, you have this system, you have input signal, output signal in lab view, which is real life. You set it up in real time. You set up a 1/t filter with Y as the input. You set up a 1/t filter with U as the input in lab view. Okay, so this is set up in real time. You get these signals coming out, all right, your R, and if you knew exactly these perfect numbers to multiply, you put them in, you exactly get the perfect control law that you want. So clearly this is realizable. Okay, so this is realizable. So as I said, the other way, okay, to note this now is that, remember, these signals are generated by us. Okay, P, the DTT operator operate on omega sub y. We just label as that. It just comes out. Okay, you don't have to separately do the differentiation. It just comes out of your state variable filter. This first signal, this second signal. Okay, third signal, fourth signal, and also RT, which is a signal. All right, you put these numbers down here. These are your signals which you have generated or you have. All right, these two signals from the first state variable filter, these two signals from the second state variable filter, this one your output signal. Then you know you needed to put in these numbers exactly. F1, F2, G1, G2, K star. And you can now very clearly see that this is your set of perfect control gains, which is, all right, we have always labeled it as theta star. And these are the set of signals that we're using, which we will label here as omega. And I put a bar here just to remind ourselves that we put in the R and we put in the K star. Okay, so this is the perfect control law. This is the perfect control law. Then again, okay, as usual, we don't have these numbers. But we know this control law works. We know this control law works. So it's exactly also as in this diagram. We know this control law works, except we don't know these numbers. Similarly, we don't know these numbers. So we will put time varying gains. All right, we put time varying gains and we will have to specify how we adapt this time varying gains, right? Okay, so basically this is the structure. So what you are then doing is you're not saying that, look, okay, I don't really know what are the perfect gains, but I know the structure. Okay, so basically what you're doing is you copying the structure and you're putting in time varying gains. And if you put in time varying gains, all right, time varying gains down here, okay, first time varying gain, second time varying, third, fourth, fifth, you just can call it theta bar t. All right, so that's exactly what we're doing. Okay, we call it theta bar t. All right, theta bar at time t. Okay, and it's we take the set of gains, multiply, but these are the set of signals we have. This set of signals we have because we generate them. We generate them, right? These two from the first state variable filter, this second two from the second state variable filter. This is our command signal we have. So these are set of signals we have. So our control law that we will use follows the structure, but we put in time varying gains, and it's exactly like that. All right, this is a perfect set of control gains. Then you go and look back. All right, this is the perfect control law. If you now set it up properly, rearrange it. All right, take this exactly as what you want. Minus a k star r plus a k star r. All right, if I minus a k star r plus a k star r, I don't change a thing. My u itself, all right, I've already decided I will follow the structure, except I put in time varying gains. All right, but the moment I rearrange it like that, you can see this was exactly, all right, my perfect set of control gains with a minus sign. So now this part is minus theta bar star transpose omega bar from earlier. All right, a very simple rearrangement. Okay, I didn't push on to do it last week, but straightforward. By this time, you should be able to do it. I leave it to you to handle it for yourself. Okay, so clearly, you know, this now if you go and check carefully from above, this is exactly theta star bar transpose omega bar, exactly what we said. Okay, plus a k star r plus u, but u we have already decided to be like this. Okay, so there's a minus theta bar star and a theta t. So you can clearly see after we rearrange, all right, exactly like this, you now get phi bar, all right, phi bar function of time, which is the parameter error. Okay, phi bar will be just theta bar minus theta star. That's a parameter error, all right, in the usual way that we have developed, except this is now done in the context of with only input output measurable. But the ideas and essentially even the methodology of algebraic working follows along the same line. So this becomes theta phi, okay, the parameter error transpose omega bar. All right, the k star r remains down there from my plus and minus. All right, and then what happens now is that it becomes like this. Okay, it becomes like this. You can do a quick check. You can do a quick check because if you now are able to perfectly put theta star in here because you knew all the gains, if you perfectly put theta star, theta bar star as your control signal, this is a control signal, this is a control signal. All right, so if you put exactly perfectly theta bar star here, okay, this will be exactly theta bar star, which means your parameter error is 0. All right, the moment parameter error is 0, it collapses exactly to what you want. Okay, the reference model polynomial, which you want as a closed loop. Rm, you will specify of degree n star, stable Hurwitz. All right, you will specify this. So the moment parameter error is 0, it collapses to Rmy equals to kp k star r, exactly as what we had wanted. Okay, but sorry, parameter error is here. And now reference model will be this clearly, right? Where Km is actually kp k star, right? Okay, reference model will be this. And you will set up a reference model. All right, RM you choose. Obviously, you would choose the KM such as steady state gain equals to 1. Okay, so that essentially you can easily work with this. Okay, you'll be working with this, as I say, also in your CA1. So it becomes very clear to you. Okay, so this is what you choose. Okay, this is what you're getting now as you do the control. You haven't done the adaptation yet. You just specify the control equals to this. All right, and then after you rearrange, you will see, all right, you check the tracking error. All right, from above, you see tracking error now comes out to be this equation that is RM. Your reference model polynomial operate on the output error, all right, E1, which is the output tracking error, equals to KP phi bar transpose omega bar. It comes to this, all right, and we now will have to work with it. So this was what we did up to last week. All right, up to last week. And you also saw that I uploaded an equivalent file. All right, it's exactly equivalent, except that essentially what had happened in the notes, you will find that adaptive control is quite interesting. All right, by and large, it is still very much a research effort. So much so that even the notation adopted depends on the books that you look at. Essentially, there are two main groups. And it also boils down to East Coast of the United States and West Coast. So this is pretty much from the book, much of the book, particularly, and also the European and the West Coast, the way they work is quite close. So this is from this terminology here from the Carl Ostrom book, the European book. Whereas I'm more used to our East Coast of the United States way of doing it. So East Coast of the United States, we tend to use the symbols omega sub y and so on. Omega sub y, omega sub u. All right. But the Europeans, the West Coast of the United States, they tend to prefer, instead of omega sub y, this omega sub y, they tend to prefer y superscript f. Instead of omega sub u, they tend to prefer u superscript f. All right, R is still there. Essentially same set of signals. So there in the notes, I had kind of used the Ostrom book. So that's why I equivalently developed this second set of equivalent notes. All right, where there I use the European notation, so to say. Right, and it's the same thing. All right, so you follow the European notation if you want. So here we follow the European notation in generating the. So as I said, you're using the European notation, instead of calling omega sub y, is y superscript. All right, but it's basically the same thing. Okay, exactly the same thing for the second order case. You set up the filter with y as the input. All right, so this is the notation following the note, so at least there is also in parallel. Then same setup in control canonical form, right? Then the 1/t filter with u, right? This omega sub u, or using the European notation, u superscript f. All right, same thing, everything same. All right, and then again comes to the same diagram, right? Exactly same diagram. And as I said, the diagram is important. All right, so that you can see, first of all, that clearly this whole thing is implementable, realizable. That's the first thing. But far more important than that, all right, far more important than that is one more thing that I want to say. Okay, let me now reduce it a bit so I can see more. Okay, there's one more thing, very important thing that I want to observe down here. Okay, which comes out afterwards in this file, in the later part of this file. Okay, so clearly, all right, system that you're trying to control, you have U, you have Y, you set up the state variable filters for 1 over T. All right, in control canonical form, these are the signals that you get. This is the structure. All right, and you know that with this structure, you get the perfect control law. If you put in the perfect numbers, you exactly get the closed loop that you want. That's the first thing. All right, that's the first thing. Okay, so you stare at this thing, but more than that, okay, so this is perfect control law. More than that, okay, before we go on to talk about the how to set up the adaptive control, if you stare very, very carefully at this diagram, okay, two very important results are embedded in this diagram, okay. The first result, which I told you, I said it will be interesting. All right, it will be interesting, I promise you. And you will see it here. All right, so go back to the diagram. All right, so remember, this is now developed for a second order system so that we can clearly see actually what happens. So this is now a second order system, right? As in the way that we have set it up. The second order system, okay? This is second order system, you have U, you have Y, okay? Then what happens is that you set up the 1 over T filter, you set up the 1 over T filter, here with Y as input, here with U as input. Here two signals come out, here two signals come out. Okay, it turns out that these two signals plus these two signals that come out, so remember here order equals to 2, N equals to 2. All right, N equals to 2. N signals come out here, all right? So N equals to 2, 2 signals come out. N signals come out here too, N equals to 2, 2 signals come out. You go and double check, all right, even though we developed this for a second order system, this entire thing, this entire concept generalizes to N order. If you have an N order system, you set up an N order 1 over T, N order 1 over T, N signals will come out in the way according to your controller canonical form. And other N signals will come out in that way according to your controller canonical form. All right, you just do it properly. So order N signals come out here, N signals come out here. So N signals, 2 N signals. These 2 N signals are not anyhow. They have a specific property that if you look there at them very, very carefully, all right, which is my first major result, that these 2 N signals that you generate, okay, the first set of N signals come in from the 1 over T filter with Y as input. The second set of N signals come in over here with 1 over T with U as input, 2 N signals. You write this down here. These 2 N signals, you can suddenly carefully show that actually they are not anyhow, they actually form a state vector of your system. Your system, okay, your system to begin with, okay, you generate those things, these 2 N signals actually form the state vector of your system, except it's 2 N order. You already knew your system was N order. So if these things are also the state variables of your system, clearly they are 2 N order, they will actually be still a state realization of a system, but a non-minimal realization. Okay, so this is very exciting, okay? Because, you know, you go back, all right, when you first study linear systems, everybody is very frightened of non-minimal realizations. And every time they get non-minimal realizations, they try to run away from it, but you know, if you are, I mean, many of you said, you know signals and systems, you know linear systems. Okay, never mind. I accept that you know. So here, go back and relook at everything that you know. Okay, you go and check. Okay, and this is the first important result. All right, if you stare carefully at this diagram, all right, you will be able to establish that, okay, if I set this thing up in this way, this N signals plus this N signals are 2 N signals that come out. These 2 N signals have the property that together they will form the state vector of my original system, except that it will be a 2n order non-minimal realization. Okay, so that's something. Well, if you look at it on hindsight, okay, and we will talk about how to establish this. All right, it makes sense. But you know, to begin with, in some ways, you could almost say that it's unexpected because, as I said, you know, if you follow standard linear systems, when you only have input-output measurable instead of the full state measurable, the attempt was always to try to construct an observer. But here you cannot construct an observer because you don't know the system. So that's why we have to go through this alternate way. All right, and suddenly we can still get the state variables equivalently of the system, except that it's of a non-minimal realization. That's the first thing. That's the first thing. Okay, now study this very, very carefully, which is why that was all I wanted to leave you all with up to for last class, because you know, you really, if you think about it, these are some very, very important and deep ideas come in here, which can actually be used when appropriate, when you can now reuse it. All right, because not often that it comes up this way. Okay, that's the first thing. So therefore, these 2n signals are state variables of the system to begin with. That's the first thing. Okay, if these 2n signals form the state vector, these 2n signals form the state vector, and you take the state vector signals, which means that all of these are the state variables, except state variables of a 2n order non-minimal realization, right? You take all these signals, all right, and then multiply them by gains. What are you doing? You take all these signals, which are state variables, and multiply by gains. What are you doing? Should be perfectly familiar to you, all right, from your linear systems. Even my 4302 students can tell you, you take state variable signals, multiply by gains. What are you doing? You are doing state feedback. So this is also doing state feedback, except that it's doing state feedback in a 2n order non-minimal realization, which now brings me to my second very, very important result. All right. So because I'm going to develop the adaptive control, and before I do that, I need to establish all these results in place. So this is proposition 1, and I will talk about establishing this shortly. All right. And proposition 2 looks at that diagram exactly as I told you to stare at for the whole of last week. It says, look, you know, you took the state variables, you multiply them by gains. So basically, you're doing state feedback. Okay, go back and study again your linear systems. All right. All right. Whether it's your 5101 or my own 4302 students here, Yanhan, Jiwen, they will remember. All right. If you take state variables and state feedback does not change the order of the system. Okay. So now go back again to the diagram, because the diagram is very important. That's why, you know, so you're doing state feedback here, except of a 2n order non-minimal realization. And state feedback does not change the order of the system. So basically, after doing state feedback in this 2n order non-minimal realization, system remains 2n order. So where are all the 2n order closed loop poles? Okay, this is now, all right, answered by the second important result, which is proposition 2, that hey, if you want to find where the 2n order poles are, they are all there. They are at the location of TP, which to begin with was the state variable filter 1 over T polynomial you chose. All right, they are also at RM, which was your closed loop reference model polynomial that you chose. But in this way of doing things, all right, you're also stuck with the fact that the zero polynomial is there, which clearly means that this way of doing things restricts you to working with systems for which the zeros are stable zeros, so-called minimum phase system. All right, never mind, next week we'll talk further about, you know, in general, if you need to do this for non-minimum phase systems. There's some other ways to do it, except it's not as powerful, not as rigorous. Okay, but you stare at this thing very carefully. Remember, I told you last week, I said, look, look, look. You stare at the diagram, I said, look, the observer is there, except it's embedded. Okay, you stare at this whole thing carefully. It's exactly the equivalent of your so-called Kalman separation theorem. Okay, exactly your so-called Kalman separation theorem. Your observer polynomial is basically your T polynomial. So remember Kalman separation theorem of linear system, observer polynomial remains there. All right, and then the rest of your closed loop poles are here. All right, which is the other part from Kalman separation theorem. So you can see down here. So equivalently then, in this approach in how we do it, the observer polynomial is there, and essentially your observer polynomial is your T polynomial. And that also, all right, highlights for you some implications, because T is a design choice, RM is a design choice, ZP is a constraint in the system that we have to work with. Okay, so I want to get on to the important result of developing the adaptive control law. So what I'll do is, okay, so exactly as what we've seen, all right, change to the European notation as we said before, right? You start with the system, differential operator form, okay, the Diophantine identity or whatever, right? Rewrite, do your operator theory, do it carefully. Then you see the perfect control law, rearrange, and you see it comes out like this, right? Control law comes out like this. Okay, we are going to look at how to set up the adaptive controller. All right, it does turn out in two separate ways, the adaptive control law, depending on the relative degree. All right, let me move past this part first. Okay, I'll come back to this. Okay. You rearrange, as I said, you can see, as we saw, the aerodynamical equation that came out was this, as I said earlier. Okay, then in order to be able to now develop the adaptive law, as I said, we needed the two intermediate results. All right, the first one that, okay, all the signals that you generated were actually the state of a non-minimal 2n order non-minimal realization. Okay, so we said that, okay, it's not difficult to prove. Okay, so go ahead. I would expect you to work on it. You will also see that in your CA1, you'll be working with this. And if you look carefully at the detailed CA1 report, which I said was there by my earlier GA, Dr. Sun Lu, you will see that I asked Sun Lu to carefully show the proof of this proposition for you too. All right, for you all. But basically, it all boils down to taking those things carefully. Okay, if it's a state variable of the system, you must be able to rewrite it. Okay, because if it's really state variable, you must be able to write the state variables. All right, even my 4302 students know if these are really state variables, okay, when you rearrange them, all right, by the time you rearrange them, if they're really state variables, you must be able to write them on the left-hand side, all right, with first derivative, and they must appear on the right-hand side again with the external signal, and you just go and rearrange and put together all these horrible polynomials down here. All these horrible matrices down here, and this relevant input vector down here. Okay, it's not difficult. Basically, you just have to work at it and rearrange. And certainly, I expect you to be able to, since all of you came here telling me you can do linear systems. All right. So this should be, you should be able to do this. Okay, so that proves proposition 1. Okay, proposition 2 is also straightforward. The moment you prove proposition 1, you will get all your matrices, and then your state vector, 2n state vector, you multiply by the gains, you put them in. All right, and again, similarly, all right, it is equivalent to state feedback, except state feedback in the 2n order realization. All right, so you again carefully put them together and arrange them and go and carefully now compute and check them and you'll find all your 2n poles are there. Of course, they have to be there because state feedback doesn't change the order of the system. They are all there and they are at TRMZP. And that essentially would establish your proposition 2 for you. And with that, then we will be ready. This is a straightforward corollary, all right, to now set up our adaptive control and then prove that really everything works and that tracking error goes to 0 exactly, perfectly, okay, according to the theoretical developments, and you will also see that in your CA1. Okay, with that, I think I want you to think about it. Let me pause. Okay, 6:55, let's start again. So remember what we're doing. We now developing the situation where we are going to do adaptive control with only the input-output measurable, right? So what you do is you set up a 1/t filter, you set up a 1/t filter, both in control canonical form, n signals come out, n signals come out, right? There exist perfect numbers to make this exactly what you want. So this structure works. But because we don't know these perfect numbers, we put in gains here and make them time varying. And we have to say how to make them time varying and show that it works. All right. But meantime, before we go on to that, okay, we know that these two results are there. First of all, that these 2n signals that you generate, all right, the 2n vector is actually a state vector of the system. All right, but it's a state vector of the 2n order non-minimal realization. Okay, then because now this is equivalent to state feedback, all right, if you, and we should be able to locate, all right, state feedback does not change the order of the system now with the 2n order non-minimal realization, the state feedback in there, you need to be able to find all those 2n poles in state feedback, they are there. Okay, remember that this result, these two results that I've just mentioned, all right, these two results that I've just mentioned is valid for a given n order system, all right? For a given n order system, all right, when you set it up in this way, for a given n order system, all right, for a given n order system, when you set it up in this way, those two results are valid, okay? And you can prove them, as I said, you know, not difficult because it builds on linear systems, right? Okay, so we're going to show how the whole thing forms into an adaptive controller. All right, let me scroll right to the end first, which is the summary. All right, and for this first part, all right, for this first part, because we have to develop the adaptive controller, the adaptive law, all right, based on the stability analysis using strict positive realness, this particular adaptive law, okay, this particular adaptive law is valid only for relative degree 1 cases. All right, but you can see it's exactly the system that we have. Okay, ignore adaptive law first, ignore adaptive law first. Okay, system given to you of order n. You set up a first state variable filter of order n. you set up a second state variable filter of order n. 2n signals come out, you put in the R in as well. All right, you can generate the signals in this way. And you know that these 2n signals, ignoring the R, are actually the state vector of a non-minimal realization of the system. And the fact that this control law, all right, for this control law, perfect numbers exist to get you exactly the closed loop that you want, remains correct, and is correct no matter what, as long as the order of the system is n, okay? So up to this part, the system, the control works for n order system, okay? No restriction. It's only when you move on to this particular adaptive law, all right, because we're going to establish stability of the adaptive law and convergence, that this requires the restriction of relative degree equals to 1. All right, and then we'll be able to establish a result that all the signals are bounded. All signals are bounded exactly as before, and tracking error goes to 0. Okay, so your CA1 will investigate that. Okay, in the early years, I made the 6104 people suffer more because you can establish a similar result for relative degree greater than 1. All right, except that you no longer can appeal to strict positive realness. So the adaptive law does not come out in so simple a manner. A lot more signal processing is required. So in the early years, 5104 people handled this without the additional very tedious signal processing, and were able to see these beautiful results in CA1. 6104 people still saw the beautiful results, okay? But I forced them to handle the more difficult case of relative degree greater than 1, all right? But you see, insofar as the system, the control is concerned, it doesn't matter whether it's relative degree 1 or relative degree greater than 1. This, up to this part, the control, everything works as long as it's of order n. Doesn't depend on relative degree. It's only the adaptive law that, you know, if it is relative degree equals to 1, because you can use strict positive realness, it comes out in this very, very elegant, direct form. With relative degree greater than 1, you have to do a lot more signal processing, all right? And it's quite horrible lah. You still see the result, and that was what I used to force 6104 people to do, but I thought in the end, no lah, no point lah. I mean, signal processing, programming it is not difficult. All right, the main thing that I want you to see is how this thing adapts and the beauty of the adaptation. So I think from 2 or 3 years back, 5104 and 6104 people in your CA1, both of you all will work with relative degree 1 system. All right, you work with relative degree 1 system, except for 6104 people, I push you to do more investigations. And as I say, it's not just the more investigations, all right? In that more investigations, I expect you to explore and see additionally what's happening, okay? So from 2 or 3 years back, both 5104 and 6104 people, CA1, you're still doing relative degree 1. Okay, but I want to again emphasize that insofar as the control law is concerned, it's the same control law, because you go back and check when we developed the control law, when we developed that important diagram that I mentioned, okay? This didn't depend on relative degree. It will work for any n order system. So with that, then what happens is that, okay, up to this part on developing the control law and the fact that proposition 1 says that this forms a state vector, proposition 2, the 2n poles locate all for you. That is true, all right? And it does not depend on relative degree. It's only when you move on to the adaptive law, because now we, first of all, for this very, very direct and very beautiful adaptive control law, you need to use strict positive realness. So this is where relative degree 1 comes in, okay? Next week, I'll talk more about the additional signal processing that's necessary for relative degree greater than 1. But you will see, I mean, you know, it's just a lot of messy signal processing. It's not difficult to do, it's just messy, okay? So now, okay, this is the way that you will do adaptive control for a relative degree equals to 1. All right, the control works for any relative degree, but because the adaptive law needs strict positive realness in this case, all right, therefore this result is for relative degree equals to 1. Okay, with that, I say all these things work, right? Summarize down here too, right? System completely uniformly stable globally, no matter where you start, okay? No matter where and no matter when you start, okay, uniformly globally stable in the large, and tracking error is guaranteed. All right, so how can I guarantee that? Okay, which is what I will do for the remaining of today's class. With that, please pull up your note 04. All right, and then now I will start developing the full set of stability results. All right, so you can look, okay, in how we have done the adaptive controller. So remember, exactly, we started off with this system, right? We started off with this system, okay? So clearly, right, this system that we start off with, okay? From proposition 1, we have generated all the signals, right? We have generated all the signals from proposition 1. It says that the signals that you generated, all right? So I will still use what I am very, very comfortable with, the notation. Otherwise, I will forget. All right, remember the 2n signals that we generated with the 1/t filter. First set of signals with y going to the 1/t filter. Second set of signals with u going to the 1/t filter. Then remember, I collected them, the 2n signals. I call them the omega vector, 2n dimensional. And remember, proposition 1 said that this was actually a state vector of the system, except it's non-minimal realization. All right, if it is non-minimal realization, then, you know, basically the proof of proposition 1, when you go ahead and you put together, you know, basically carefully constructing the matrices and putting them together. All right, if indeed, you know, based on that, definitely because it's a state realization of the system, therefore is that system matrix A. And to emphasize that it's a non-minimal realization, I'm going to carry triple bar with it so that I don't forget it's a non-minimal realization. All right. And equivalently, in the proof of proposition 1, you can begin to fully write out your BP triple bar and also CP triple bar transpose. All right. And your 2n set of signals. All right. And that's from proposition 1. Okay. Then basically we were using this in the control law. Remember, we were using this in the control law. Exactly this 2n order set of signals. We were exactly using this in the control law. All right. Of course, with the R and the KT. All right. Then you also saw that, okay, we use this structure, exactly the structure. All right. Exactly as you saw. All right. We use the structure. And in the structure, okay, if you knew the exact numbers, it would be theta star. So similarly as before, of course, I can also write and separate this out as theta star, all right, transpose, all right, plus the parameter error part of it down there, okay, which is arising from the fact that I put in the time varying numbers, okay, and similarly also for this part, all right, I separate out the perfect number, K star, plus P, all right, also the parameter error in K, right? So it will be exactly like this. Okay, then, okay, I will now go on carefully, right? Carefully now tracking all of that. Now all the time reminding myself carefully that I'm working with a non-minimal realization, all right? So that I don't forget. Okay, then go ahead. You saw the U how we have done it, right? You saw U. Okay, with the U, we separated it out like that. All right, so here we separated it out and put it down there. Again, reminding myself here of the non-minimal realization, right? And then if I rearrange, okay, rearrange with the theta star part, pulling out the parameter error part. All right. In quite a parallel development, right? In quite a parallel development to what we had done before. Okay, now clearly you will be able to see that, look, you know, to begin with, realizing that it was a non-minimal realization, there will be an equivalent AP triple bar, all right, which was from above. All right, and when you prove proposition 1, you will exactly have to put down together carefully the details of AP triple bar. So it's all there. All right, so there's AP triple bar. Then, okay, there's also BP triple bar. When you prove proposition 1, the details of BP triple bar will come out. We also know there's a perfect control gain theta star. All right, and then K star, okay, this is again from the non-minimal realization. All right, that'll be there. This again from the non-minimal realization. Okay, remember here, this is from the non-minimal realization of the system. You're putting in the perfect control gain. All right, and you saw that this was perfect control gain gave you state feedback in the 2n order non-minimal realization system. And when you put in these perfect numbers, all right, it gave you perfectly now, all right, the state feedback in the 2n order system, all right, and you can locate all the 2n poles according to proposition 2, so that you will be able to, in the result of, as a consequence of proving proposition 2, you will be able now to write out fully what is the equivalent non-minimal realization closed loop of 2n order. And this one, the poles will be exactly the 2n poles that we saw coming out of proposition 2. And it will be AM triple bar. All right, then similarly, all right, all of those, all right, with the perfect numbers, this will be BM triple bar. All right, K star operate on BP triple bar will be BM triple bar. And this one now, all right, will be the same. It will be CM triple bar transpose. All right, this is just to remind myself that once I have the perfect control gains and I put them in, I now exactly should have, all right, the reference system that I wanted, but also now in 2n order non-minimal realization. So even the closed loop reference model is in 2n order non-minimal realization. Okay, think very carefully. There are implications down there. All right, implications down there. And if you think very carefully, you might be tempted to say, hey, it's very similar to adaptive control with full state variable measurable. And indeed, there are similarities. But that's why I want you to think carefully. There are also key fundamental differences. All right, which is why even though there are things which look similar, yet it is totally different. All right, I leave you to look carefully and think carefully. Okay, so okay, beginning to look at propositions 1 and 2. All right, basically now exactly when I have the triple, AM triple bar, BM triple bar, CM triple bar, it exactly gives me, all right, my reference system. All right, except that, you know, it collapses to this system. Okay, completely possible. All right, but basically, all right, when you want to expand this out and write this fully in 2n order non-minimal realization, it will be exactly this thing. All right, but when you go and now actually compose the transfer function, all right, basically it simplifies to this. And therein is where, you know, you need to watch that very, very carefully. So therefore, what this says is that indeed, you know, this reference system that I'm going to use, which is an input-output reference system, itself admits a 2n order non-minimal realization, which now, all right, will exactly look, all right, so I will have to write it down. Okay, this will be the reference system, all right, but now written in 2n order non-minimal realization. All right, 2n order non-minimal realization. Okay, and the associated matrices for this 2n order non-minimal realization will indeed be AM, And to remember it's not a minimum, I put the triple bar. All right. Plus, all right, BM triple bar CM triple bar transpose. All right. And then this AM, BM, CM exactly comes from, all right, what I put in here when you put in the exact theta star gains, all right, the perfect gains. And this is exactly what it comes from. It's exactly that. Okay, this thing therefore exists. Okay, exists. Okay, the only thing which is very fundamental twist here is that this thing exists. This thing exists, but unfortunately you cannot use this. All right. So this is where fundamentally it now totally deviates from the problem of adaptive control with full state variable measurable. Here you only can write this conceptually. You know this exists, but you don't have your hands on this set of state variable signals. Whereas in adaptive control with full state variable measurable, you were the one setting this up and programming this. All right, here no. Here, the only thing you can say is that conceptually, you know it exists and it now looks in this particular structure. Okay, so never mind. For now, for me, it's good enough that it exists. Then I go on, I said, look, never mind, I know it exists. So similarly, since it exists, I still can track a conceptual state tracking error. Okay, so this one, I know it exists. All right, I myself cannot put my hands on it and use this signal, but it exists. This is from the reference system. Okay, then of course the 2n signals which I generate. All right, first of all, the n set of signals with 1/t filter with y as input, another 2n signals with 1/t with u as input. So these are 2n signals I generate. This one, of course, I have because I generate them. Okay, this one exists conceptually. Never mind, exists conceptually, I can still define a state tracking error. All right, it's still correct, even though now I no longer can use this because I don't have this omega sub m. Okay, then I also can identify an output tracking error. I can identify an output tracking error E1, and this one, of course, I have because output, all right, you told me y is measurable. And reference model, I'm going to generate. Reference model is generated in a very simple way, just like this. All right, just like this. All right, with Rm equals to relative degree, and Km you would choose just to make sure steady state gain equals to 1 so that it's easy for you to work with. So this is what you generate. This is what you generate. So Ym you have. Okay, Ym you have. So therefore, E1 I totally have. Okay, with this now, and with strict positive realness, I will be able now to properly show that indeed I can have that beautiful, elegant adaptation. All right. So again, as before, from above, I can now take the state variable descriptions, subtract one from each other. So in this up to this point, the development is similar, but the details are fundamentally different. Okay, so with that, I can still write the trait error, except that this is non-minimal realization. So I remind myself, all right, I remind myself, and I remind myself. Okay, and then of course, what happens down here is, okay, now let me write in the tracking errors, the parameter error, sorry. So clearly there is the parameter error associated with the set of signals with y and u. So that will be phi, all right, in transpose form. And then, of course, the scaling gain. All right. So let me now collect all of that together. All right. Because this will be of 2n dimensional. This will be basically the scaling gain. All right. So this 2n plus 1. This is 2n dimensional. This 2n plus 1. So let me call it phi bar. Let me call it omega bar. All right. So now, once I have that, basically, conceptually now I've reached this stage whereby I have this and I can write it out in this particular form now. Okay, but be very, very careful. All right, so conceptually, it now looks like this. Okay, these are the non-minimal realization, right? These are the non-minimal realization. So conceptually, you can write it down. Conceptually, you can write it down. All right. And even more than that, all right, from propositions 1 and 2, from propositions 1 and 2, and from what we had developed, all right, we also know, as I said, you know, with this set of matrices, all right, this set of matrices, remember, they're coming from the perfect set of gains, all right, AM, triple bar, BM, triple bar, and CM, triple bar. So as a triple, all right, as a triple, they form the reference model, all right, and now if you compute out the transfer function, all right, of this triple, all right, transfer function computation is straightforward. From linear system, it will be CM triple bar transpose SI minus AM triple bar. Remember, this is all in the non-minimal realization. All right, and this will now turn out to be, all right, you're going to check that carefully because it's the exact set of perfect control gains. All right, this will now turn out to be Km over Rms, because that's exactly what we set it up to be. All right, okay, this is where, if I now proceed on, it becomes different. This will now be, all right, strictly positive real, all right, for the case with relative degree equals to 1. All right, you can check that. You can check that because relative degree is n star. All right, Rm will be of degree n star. So this will be basically just a first order stable polynomial, Km over that. All right, and this will be strictly positive real for a stable system. All right, strictly positive real for a stable system, but only if you're talking about relative degree equals to 1. Because actually up to this point, if you didn't bother with relative degree, up to this point, this everything is still correct, all right, for any relative degree. All right, up to this point, everything is still correct for any relative degree. It's only that when you now say that, okay, this particular transfer function operator is strictly positive real, then you're working under the assumption that it's relative degree equals to 1. All right, now with relative degree equals to 1, I can proceed further. All right, because now, as I said, if you now look at our summary, all right, with relative degree equals to 1, we are saying, okay, our adaptive law now can be as straightforward as this. Our adaptive law can be as straightforward as this. Okay, and now that, all right, so you see adaptive law, exactly as we said, all right, is like this. Okay, so this is now the 2n signals, all right, which we generate, plus the R signal. So this 2n plus 1, all right, exactly as before. Right, the 2n signals that we generate, plus the R signal. All right, and we are adapting it like that, minus signum Kp, symmetric positive definite matrix gamma. All right, any symmetric positive definite matrix gamma. All right, the 2n signals from the state variable filter that we constructed with the R and just the tracking error, just like that. Adaptive law is just like that. Okay, so you can see the control gains are the 2n control gains and the scaling gain, 2n plus 1 scaling gains adapted in this particular way. All right, so it's as simple as that. Okay. Now, if we say it's like this, we better make sure that it really can be like this, and that comes about because of strict positive realness. Okay, so now, okay, similarly, we'll pull down our ellipsoid function. So conceptually, this part, okay, we're using the same concept, all right, but as I said, yeah, you have to be very careful. Conceptually is the same, but some very, very important details fundamentally are different. But never mind, we use this ellipsoid quadratic form. All right. And then because now we know that we are working with relative degree 1 system, we also know that now we can use the horrible Kalman-Yakubovich lemma, right? Remember what that was? Okay, remember also that now we are working with the positive real system comprising of this triple, AM triple bar, BM triple bar, and CM triple bar. There's no direct feed through. That means the direct feed through term is 0. Direct feed through term is 0. So I just have a strictly proper system here. Okay, then I go back to my Kalman-Yakubovich lemma. What did my Kalman-Yakubovich lemma say? All right, with no direct feed through, basically I have AM triple bar transpose P. All right, P exists. AM transpose P plus P AM triple bar will be equals to the diet Q transpose, right, minus an epsilon, which is a positive number, L, which is a symmetric positive definite matrix. And here, basically, you can just simply write it as, again, Q, which is a symmetric positive definite matrix. Okay, so we have that. But remember, we have one more thing, all right, from Kalman-Yakubovich lemma, which I will reserve for use shortly. Okay, so, okay, we have that. So as before, I do the same thing. All right, so I substitute those things in carefully with the arrow equation. This will be now AM triple bar E plus 1 over K star, right? This is plus 1 over K star B triple bar, all right? V bar transpose omega bar. Okay, so I have that. And of course, the rest of the terms. Okay, then as usual, I follow that decomposition, right? I follow that decomposition of this matrix into AM transpose PAM, all right? Then once I do that, what will happen is that this thing will now decompose into as before. Okay, I'll let you check that out. Minus E transpose QE, all right, minus E transpose QE. Then you can also double check that. Okay, the E transpose will come out with 1 over K star P. All right, BM. I should be careful down here. All these things are the non-minimal realization. All right. BM. All right. So you can carefully check that. Right, and it comes out to this, all right, with the decomposition. Okay, then of course, if you note from above, Km was Kp K star, all right, it was there. Lost it. Anyway, you can check. Km is Kp K star. All right, that's how we set it up. Km. Implicitly possible right here is that. K star. Kp K star. Right, because you can see, right, this whole thing comes out here to be Km over that, so you can reverse track. All right, I'll let you reverse track that now this Kp K star will come out and it should directly come out to the Km, all right, giving you that perfect control gain. Then with that, okay, what you do is you go on, all right, noting that Km equals to Kp K star, we will use now the second property of the Kalman-Yakubovich lemma, all right, that says now that, okay, with this transfer function that you have, all right, which has, okay, this transfer function has the state realization, all right, has the state realization as we saw from above, AM triple bar, all right, which is the AM matrix, 1 over magnitude of K star, all right, BM triple bar, all right, and of course CM triple bar, all right, this state realization, okay. Recall that in the Kalman-Yakubovich lemma, there were two parts to it. All right, the first part was that AM transpose P plus PAM equals to minus Q transpose minus epsilon L equals to minus Q. First part we have used already. Okay, but remember there was that second part which also says that this P that you're able to compute, this P that you're able to compute, all right, he says you go back and take it back with the B vector in the state realization. All right, this is a B vector in the state realization. Remember, all these things are, again, non-minimal realization. So let's not forget. Okay, so remember that there's a second part in the Kalman-Yakubovich lemma that says, okay, now that you have this, all right, because remember, all right, what we have with the perfect control gains, right? These were the perfect control gains. All right, if you put in the perfect control gains, right? If you put in the perfect control gains, you get AM triple bar, BM triple bar, CM triple bar. And you also knew that, you know, from there, all right, when you get these things with the perfect control gains, all right, what then happens is that with the triple, AM triple bar, BM triple bar, CM triple bar comes up to be KM over RMS. Okay, it comes up to be equals to this, and this is strictly positive real. So then what we do is we use exactly this strictly positive real system, go by the Kalman-Yakubovich lemma, all right, for this system. So first of all, we already got this first part for the AM triple bar. All right. Now we will go back, okay, and use the remaining parts, okay, with no direct feed through. So remember, what we also have was that the P that you calculate, okay, the P that you calculate, remember from Kalman-Yakubovich lemma, it says you take the P that you calculate, all right, you multiply by the BM triple bar, all right, it should be directly equals to the CM triple bar, all right, with the scaling, because the scaling is such that we have a 1 over K star down here, all right? So we have a 1 over K star down here. So basically in here, in this particular set of equation that we have a 1 over K star down there. All right, so basically you have to put the 1 over K star down here. All right, so now what you have is that you have P 1 over K star BM is exactly equals to CM, and this is what we're going to use as the next part. All right. And you can check, I mean, it's a simple thing. All right, when you now, you need to know sign of KP in this system. So it's a simple thing that you can always choose your sign of KP. All right, you choose your sign of KP. You choose your KM to be positive. Basically, you will choose your KM to be positive. Then what will happen is that your sign of KP, all right, your sign of KP will just be the same as sign of K star. Okay, so it will be the same thing. All right, and then with that, you can now push on, because with the second relationship coming out of Kalman-Yakubovich lemma, you will see that this particular part, which I kind of circle out in green, this will compute to be from Kalman-Yakub-Borish lemma exactly CM triple bar. Okay, it will compute to be exactly CM triple bar. And then because it computes to be CM triple bar, okay, because it computes to be CM triple bar, okay, you look at this very, very carefully. All right, you look at this very, very carefully. It computes up to be CM triple bar. Then what will happen is that now E transpose, this E which you don't have now, but because of the Kalman-Yakub-Borish lemma, you E transpose CM triple bar now simply turns out to be E1 of T. Okay, E1 of T. And then because of the way that we have generated our adaptive law, so remember this second part is from the adaptive law, right? This is from the adaptive law. This part is from phi bar dot of T, correct? Which is how we designed the adaptive law. So likewise, you will see now that with that, then what also happens is that this cancels this, all right? Leaving us with minus E transpose QE, would then, of course, all the associated results of boundedness, all right? And you can go ahead and do the integral of the tracking error squared. Okay, integral of tracking error squared, then also checking the E dot, showing it's bounded, leaving us with all the required results, which then enables us exactly to say, as we have said down here in this, this summary, okay, in this summary, okay, that in this summary that plan, you set it up in this way for the case with relative degree n star equals to 1. If you now do the adaptation in this way, all right, I've shown you the full development, convergence, and stability analysis using Kalman-Yakub-Borish lemma. Okay, as I warned you, it was going to be very, very messy. So I've tried to keep it quite direct, all right? But never mind, okay, you will need a few more times to carefully look at it, be aware of it, and then note that, look, you know, what then happens is that you get this result for this adaptive controller, which indeed you will get a chance to explore in both 6104 and 5104 CA1. Okay, with that, I think there's again, all right, a lot for you to carefully review. Let me stop the recording again.